Hey everyone, so in this video we want to talk about friction in Vellum, and for this I have a little example here. It's just a sphere where I colorized all the primitives so that I can see better how it behaves, and then it's just a normal cloth and a default Vellum solver, nothing special, and the whole thing looks like this. Nothing really surprising since it's a simple cloth and not any kind of 3D soft body. It really just implodes because it's empty inside. Okay, what we want to talk about here is not so much the stiffness, but the friction. And you control the friction in the solver. And the easiest way is, funnily enough, under forces, there is a friction, category. And here you have multiple controls. You have a ground static and a ground dynamic scale, and this obviously is for the ground. So maybe let's start with that. What you can already see is there's a difference between a static and a dynamic scale. And that just means, okay, if an object is moving, how quickly does it come to rest, basically, how much of its energy or its movement it's losing over time, which is the ground dynamic scale. And the other one is ground static scale, which means how much friction is there as if an object is, just lying there and maybe something pushes it, for example. So most of the time, those two numbers I change together. So if I want no friction, so currently, as you can see, when the guy here rolls down, it stops at the ground. And if I turn both off, you will see that he will just slide as if it was, a frozen lake or something. So there you go. Whee! He just slides on. So this is pretty easy, and honestly, very often you don't need that. What is more interesting is the upper part. And this defines how every active object behaves. So we have here a static threshold and a dynamic scale. And the static threshold means, if you look in the description, what is the velocities that are considered static. So under this number, if something goes slower than that, then it's considered basically non-moving, and it kind of stops. So this is kind of for stickiness. So when does an object completely stop, basically, under which velocity this happens? And if this velocity is not reached, so if an object is moving faster than that, then the dynamic scale comes in, and which is the classical how much friction is there for a moving object, which is what we have here. So let's first play with the dynamic scale to get an idea what that means. This is roughly how it behaves with the defaults. And now let me increase the dynamic scale to 0.7. And the idea here is that we want it to move, but while it moves, there should be a friction on the surface. Let's increase that even further, maybe 0.85. And what I hope to see is that, here it is. The cloth basically has so much friction that it tends to roll over itself. And this is the best use for the dynamic scale. Yeah, and let's lower this to 0 again to see a comparison. And here you can see how it really just slides with rarely moving or rotating at all. Let's actually go increase it to 1 as well, one last time. And you can see it is moving, but there is a friction while it's moving. On the other side, you have the static threshold. So even if we would dial down the dynamic scale to 0, this is the velocity under which the object is considered to stick. So let's increase that to 10, let's say, a really high number. So basically everything should stick. And when we run this now, you should see, there you go. And just to be clear, this number is not the velocity of the points. It's a bit more complicated than that. The way it's described in the help is the ratio between the tangential velocity and the normal impulse. Doesn't really matter. It's just remember that you have to find the number that works for you to bring something to a complete halt when the overall speed is below that number. That's why you usually don't use this one too much unless you want 100% friction. Unless you want that, you use the dynamic scale. So this would be more for stuff that is moving, but while it's moving, it has a friction. So I have some comparisons here. So this is purely controlling the friction. So we have the defaults in the first one. Then we have all frictions set to 0, the static and the dynamic. Then the third one is no static threshold, so it never will fully stick, but it has a very high dynamic scale. So while it's still moving, it has a friction. And the last one is no dynamic scale, so there's no friction as long as it's moving, but a very high static threshold, which means it has to be very fast to not instantly stick. And those are the four that we see here. So this is a default. This is with no friction at all, which, by the way, almost behaves the same because the default numbers in some cases are pretty low. Then the third one, again, is high dynamic scale, but no static threshold, which means there's a strong friction here, but it never completely stops. And the fourth one here has a static threshold of 10, but no dynamic scale. But that doesn't matter because it instantly sticks to the ground because 10 is such a high number in the static threshold. So I hope this makes sense. Of course, it depends what you want to have. And the main difference basically is stickiness versus friction. And there is static threshold and dynamic scale. Okay, so we could finish here, but I want to talk to you about another thing, and that is you don't have to set it in the whole Vellum solver as, as a general setting for all your objects, but you can actually differentiate. And this is by not using this actually, but setting your own attributes. So if I look at this example again, this is our default settings again. And this time I don't want to change the settings in the solver, but I want to actually override the settings on the object. And I can do this with two attributes. There is friction and dynamic friction. So the first one, friction, it's a float. I set to 10 again, and this is basically stickiness. So as soon as the relative speed is below this number, then the friction will basically be 100%. So that looks like this. It instantly sticks to the surface. Now keep in mind, currently the friction is not actually 10 because this number is always multiplied with what's in your Vellum solver. So in this case that was fine. 10 multiplied by 0.5 is 5, of course, and therefore the number was high enough in our case. But keep that in mind, the safest bet when you use with attributes is just multiplying both with 1, so setting both to 1, because then the number that you give it will always be the absolute number and it will not be multiplied with anything else. So here now you can see it's even more drastic than before. And I'm saying that because next I want to show you the dynamic friction, and I set this to, let's say, 0.9. And if I run this now, you can see it still moves, but while it moves, it has a very high friction. Actually, maybe it's a bit too extreme. Let's lower this to, let's say, I don't know, 0.6. And now we should see, yeah, it's moving, but it almost at least rolls over itself. It doesn't really matter, you get the idea. Now what I want to show you, it doesn't matter what number you put in here, even if it's a really high dynamic friction. If you lower the number in the Vellum solver under forces, the dynamic scale to 0, then it will be multiplied by that. And if I run this now, as you can see, the friction is gone. So keep that in mind, it will always be multiplied. So how do I know all this? Well, there is actually a helping page about this. And this is, by the way, a relatively new thing. And the web page is called Varying Friction in the Help, where all of this is described. And it has a little example video here where they kind of paint the friction like this. My assumption here is that they actually painted a dynamic friction, not a friction or static friction. And this is, if you want, something you can do with it. Yeah, and finally, here is another example of different variations of this, where I put 3 spheres next to each other. There you go, with funny colors. And I gave a friction of 0. So again, this is the stickiness, 6 and 50. And when I run this, you can see the difference. There you go. In both cases, the 6 and the 50 were high enough to make it stick completely, because internally I set the static threshold to 1. And the same is true for dynamic friction. It follows the same logic. I multiply the static threshold with 0 and the dynamic scale is set to 1. So that means that the dynamic friction attribute that I'm setting here to 0, 0.5 and 1 will be multiplied with 1. And the whole thing looks like that. And you can see that, of course, the one with the dynamic friction of 1 is the slowest, the one with no friction at all, which by the way is multiplied also for the ground. I forgot to say that, but you can see that here has no friction at all, and this one is 0.5. Keep in mind though that this is all currently with a substep of 1. Just like with our stiffness settings, the same is true for friction. If you change your substeps, your behavior will change as well. So this is now the same settings, but with a substep of 3, and technically this is more accurate. But if we compare the behavior, you can see they actually behave in a different way. So here you can see they come to different conclusions with a substep of 1 and a substep of 3. So keep that in mind. Everything in Vellum will have different results based on the substeps, and the general rule is the higher the substeps, the more accurate the calculation. And then finally, I want to show you that you can actually not only set this for the whole object, but you can also use that to give different frictions to different parts of your simulation, which is kind of what we saw in the video from the help. So what I have here currently is just a planar patch, which I moved up a little bit and rotated, and then currently the dynamic friction is set to 0, and internally the static threshold is set to 0 as well, and it just looks like this. Whoop, it just, you know, slides off as we would expect, nothing too special here. But what I did now as an alternative to this is I set the friction based on the relative bounding box. I don't want to explain this vex too much. Let me just show you the visualization to this. And here you can see this has currently a dynamic friction of 1.5. This is the highest number. And over here, it has a dynamic friction of 0 in one geometry per point. And this is actually understood by the solver. And if you run this, you can see that there's a difference in the behavior inside of a single object. And this could be really interesting for you if there's something like that you need. So as you can see, there's a wide variety of options in the Vellum solver itself. You have kind of a general rule for the friction. Under force is friction, where you can control, okay, the stickiness basically, under which speed an object is considered sticky, and also a general friction, which is a dynamic scale, which even if the object moves, there is some friction applied. And you cannot only assign this to all objects in the Vellum simulation, but you can even do that with the help of two attributes, which is the friction attribute and the dynamic friction attribute. And this doesn't only work for different objects, but even per point. So even in a single object, you can have different friction numbers for the dynamic and the static friction. Okay, so I hope this is helpful. Thanks very much and see you later. Cheers.